Then we are going to go on to completing and balancing chemical equations, which means we are going to try to figure out which products are produced in a given chemical reaction. So, to do these, you are going to be responsible for two types in here. Those types are double displacement reactions which are also called double replacement reactions. And the other type that you will be responsible for is combustion reactions. So there are actually 5 different reaction types. Of those 5, though, these are the 2 that you are responsible for. So we'll start by looking at double displacement reactions. And a double displacement reaction takes on this form. We could say that we are going to react AB together with CD, where AB and CD are both ionic compounds. And what happens in this type of reaction is that the positive ions trade places. And if they trade places, that means that the product of this reaction, what would one product be? C, B, and AD. Exactly. So again, the positive ions trade places, and this is what we wind up with for products. So now what we're going to do is we're going to look at some examples of these reactions. And the first one we're going to look at, and we're actually revisiting these. These are some that we did earlier when we were looking at chemical change versus physical change. And the first one that we're going to do is we are going to mix together some calcium chloride and sodium carbonate. Calcium chloride and sodium carbonate. So what I'm going to do here is I'm going to come back to the sheet and we're going to write these down. Calcium chloride is being combined with sodium carbonate. And then we'll go ahead and mix them together and see what happens when we do that. So, count this out. And when we mix them together, what do we call this type of reaction again? Chemical. That's a chemical, but what is it that's taking place in here? We formed a precipitate. We formed a precipitate. They call this a precipitation reaction. We formed a precipitate. Remember that the word precipitate means literally to fall out. So we then want to write out a chemical equation for this reaction. If there's going to be a double replacement, calcium will now pair up with carbonate, and sodium will pair up with chloride. Well, now, if you didn't do well with nomenclature before, you're going to do even worse with it here, because this is where we really need to have these things down, because if you don't have them down, this is going to take you forever, and chances are you're going to get the wrong answer every time. So, let's start by looking at the periodic table and figuring out the charges on these. Charge on calcium is always going to be how much? 2 plus. Chloride is always going to be Cl with a charge of 1 negative. So if we have Ca with 2 plus, chloride with a 1 minus, that means that the formula for calcium chloride would be Ca Cl2. And because we started with it dissolved in water, the phase label is going to be AQ. We then reacted this with sodium carbonate. We come back to the periodic table. Sodium, Na with a charge of 1 plus. And carbonate is CO3 with a charge of 2 minus. Okay, so if we have a single positive and a 2 minus, that means that the formula for sodium carbonate is Na2 CO3. And because it was dissolved in water, that means that the phase label is AQ. So here's what we're starting with. So now this is going to yield. Of course, now this is taking up too much space, so I'm going to slide that down there just a bit. And then what we want to do is we want to figure out the products. So now figuring out the products, calcium is now paired up with carbonate. What would the formula for calcium carbonate be? Ca CO3. And that's because when we combine them, we have a 2 plus and 2 minus. If we have a 2 plus and a 2 minus, what happens to the charges? They balance, they cancel out. And then the other product is sodium chloride. And what is the formula for sodium chloride going to be? Well, how many sodiums do we need? 1. How many chlorides? 1. So the formula is NaCl. Well, then what we'd like to do is we'd like to figure out the phase labels. That is what goes in here. And this is where this handout comes into play. Okay, so this one right here. We want to figure out what the solubility is. Now you'll see that this is divided into 2 parts. We have the top portion, which is mostly soluble, bottom portion, which is mostly insoluble. If it's mostly soluble, that means it will dissolve. And so we come back to our products. We're going to try to figure out where they lie. So let's try to find calcium carbonate on this table. So we come back to the table. We want to figure out where calcium carbonate lies. And where would we find calcium carbonate? I don't see calcium carbonate anywhere up here. Very last row, exactly. So we see carbonates in here. So what this tells us is that compounds containing the following ions are mostly insoluble. In other words, if it contains carbonates, it will usually be insoluble, but then we check the column of exceptions, and we check to see if calcium carbonate is an exception. And is it an exception? No. So that means it is insoluble. If it is insoluble, that means that the phase label is going to be a solid. Exactly. It is a solid. And once again, that's because it is insoluble. If it's insoluble, it means it doesn't dissolve. If you want to put in the phase label for sodium chloride, we come back here. And you can actually figure this one out 2 different ways. You see sodium here, you see chloride here. But you can just choose one or the other. The results will agree, but you choose one or the other. So if we see sodium, this tells us under the mostly soluble with no exceptions. So that means if it contains sodium, it will always be soluble. And if it's soluble, that means that the phase label is AQ. And that's where sometimes students will get confused. S doesn't stand for soluble, S stands for solid. And soluble means it dissolves in water, so we get a phase label of AQ. Now we're not quite finished with this. We need one more thing, and what would that be? Need to balance it. So we check the calcium here. How many do we have? How many calciums on the other side? 1, so it's balanced. How many chlorines here?
2.
How many here? 1. So what do we need? 2. And where does that 2 go? At the front. Right. We can't change it. Because of course if you try changing it, putting the 2 down here, then you're creating something that doesn't exist. So when we balance it, we can only balance using coefficients. How many sodiums here?
2.
How many sodiums here?
2.
2. And now, when it comes to polyatomic ions, since they stay together in precipitation reactions, or double displacement reactions, we can actually look at them as a whole unit. So how many carbonate ions are there here?
1.
There's 1. And how many carbonates are here? 1. So if we have 1 carbonate on each side, it looks then that it is balanced. And this then is the balanced chemical equation for this reaction. Any questions on this one? Yes?
Would it matter if you write NaCl first and sodium carbonate?
No. Very good question. Let's say I had 4 plus 3. 4 plus 3 is the same as 3 plus 4. So the order doesn't matter. I know we learned a term for this back in 1st or 2nd grade. Forget what it's called, like commutative or something like that. Is that right? Yeah, I don't know. I remember learning that way back when, but yes, the order doesn't matter. Okay. What does matter is the order in the formula. So you would always write NaCl. You would not write ClNa. And that's because when you write out the chemical formula, which one always comes first? Positive, right. Positive always comes first. So the order within the formula does matter, but the order when you have the plus sign in there, it doesn't matter whether you would have put the NaCl first or the calcium carbonate first. Okay, good question. Anybody else? And there's a reason why I put it the way I did. We'll talk about that after the next one, though. Okay, let's look at another reaction. We are going to take, let's write down the names for these two. We have some iron 3 chloride. Iron 3 chloride. And then the other one is sodium hydroxide. And of course, if we write the name iron 3 chloride out, how do we write that number 3? Parentheses and then?
Roman numerals.
Roman numerals. So iron 3 chloride. We write it like this. And then we're reacting this with sodium hydroxide. So now, if we want to mix these together and watch what happens, and this, by the way, is happening to lots of cars out there today. You know what we made? This is rust. Okay? This is wet rust. So there's actually dry rust and wet rust. They have slightly different compositions. When it's wet, they're very similar, but different. We just made some rust here. So now, if we want to figure out what these products are, products would be iron 3 hydroxide and sodium chloride. So then we go ahead and write out a chemical equation for this. We write out a chemical equation. Iron 3 is Fe with the charge of 3 positive. Chloride is Cl with the charge of 1 negative, as we've established already. Sodium is Na with a charge of how much?
1 positive.
1 positive. And the hydroxide ion is one you were to memorize, that is OH negative. That's one of your polyatomic ions. So now, if we go ahead and write out a chemical equation for this, we start with the iron 3 chloride. So the formula there is going to be FeCl3. We need 3 of these chloride ions to balance 1 of these iron ions. So it's FeCl3. Phase label is going to be AQ. It's already dissolved in water. And then the next thing we did is we combined this with sodium hydroxide. We have a single positive, single negative. What happens? Balance each other. So it's NaOH. Phase label is going to be AQ. In fact, all ionic compounds start as solids, and so if you see them as a liquid, that means we've dissolved them into some water. So now we're going to react these together, and I'm going to slide this over a bit, give myself a little more room. Products are iron 3 hydroxide. So now we want to combine these. How many irons do we need? How many hydroxides do we need? And what do you do with the hydroxide? Parentheses and 3 down below. And then we combine these 2 together. What do we get for formula there? NaCl. Now we need to put some phase labels in. If we want to put in the phase labels, we go back to our solubility table. We look for iron 3 hydroxide. And iron 3 hydroxide, where are we going to find either one of them? Here we go. We find hydroxide, which is under the mostly insoluble. Then we check to see if iron 3 hydroxide is an exception, and it isn't. So if it's insoluble, the phase label here is S. Then for sodium chloride, well, the easiest one here is to simply look at sodium because it's soluble with no exceptions. If it's soluble with no exceptions, phase label is AQ. We're not quite done yet, so the next thing we need to do here is balance the equation. So to balance this one, we look at the irons. How many irons on each side? 1. How many chlorines? 3. And over here we have 1. So what do we need? Put a 3 there in front of the NaCl. How many sodiums do we have here?
1.
And over here? 3. So what do we need? 3. Need a 3 in front of the NaOH. Then if we look at the hydroxides, how many hydroxide ions do we have here? 3. And how many hydroxides here? 3. So it looks like we now have a balanced chemical equation. Now, as far as a couple things that we should be aware of, we go back to the question we asked earlier. Does it matter which order we write the products in? The answer to that question is no. Because, once again, 3 plus 4 is the same as 4 plus 3, so the order doesn't matter. Now this said, chemists actually do have a convention that we use in writing the order of the products. And by a convention, that doesn't mean it's a rule. What it means is it's the way that we prefer to write it. The way that we prefer to write it is that we prefer to write the precipitate first. And so I knew in my head which one was going to be the precipitate, so ahead of time I made sure that we wrote it first because it just bugs me if I see the solid last. But it's not wrong, it's just a convention that most chemists use, is that we write the precipitate first, followed by the aqueous or gas or whatever else. But again, it's not wrong if you do it, and Mastering Chemistry will grade it correct either way. Yes?
Didn't you say that the positive had to be first before the negatives?
Yes.
Then why is the O before the H?
Well, this is part of a polyatomic ion.
Oh, okay.
So it's part of a polyatomic ion. That is the formula of the polyatomic ion.
Okay.
So it doesn't matter there. Within the ion itself, we have that different order, but you still have the positive ion before the negative ion.
Oh, okay.
Okay. Anybody else? So then, if I come back here and ask you, this is the last one we looked at, what is the formula of the rust-colored stuff in here? Or what is the name of the rust-colored stuff that's in here?
Iron hydroxide.
Yeah, iron hydroxide, specifically iron 3 hydroxide. And if we wanted to get the iron 3 hydroxide out of here, what would we need to do? How could we get the iron 3 hydroxide out of here?
To dissolve the sodium chloride.
Now it's already dissolved. How do we get a solid out of here? Again?
Filter.
Filter it, exactly. We just we'll pour it through a filter, and where would the solid be? In the filter. And what would go through the filter? Liquid. And what would the liquid contain in this case? Sodium chloride. So that's, if you want to think about what kinds of questions could he ask, he as in me, that would be an example of a type of question. What is it that passes through the filter? And again, what would pass through the filter in this case would be sodium chloride. The stuff caught in the filter would be the iron 3 hydroxide. Okay, any questions? Which stuff has precipitated and settled to the bottom of this? I don't know if you can see the solid down there. What is the solid that's at the bottom here? Calcium carbonate. Right, calcium carbonate. Okay. Let's take a look at another one. One more, and then we're going to practice some. So in the next one, we are going to take some, what do I have? Potassium iodide. Potassium iodide. And we are going to mix this with some sodium carbonate. So potassium iodide and sodium carbonate is this next mixture. Now, we go ahead and pour them into here. And then we are going to mix them together. And we want to pay close attention to what happens when we mix these two together this time. So if I pour one into the other, again, watch carefully. And when we mix them together, what happened? Nothing, right? Yeah, nothing. Nothing interesting, or just nothing, period. Nothing happened. So, if nothing happened, then this would be a case for what we say is no reaction. And it's actually one that we would be able to predict is no reaction. But let's see how we would actually be able to predict that this is no reaction. First of all, let's go ahead and write out the reactants. We have potassium iodide. So potassium is K with a charge of 1 positive. Because potassium's here in the periodic table, everything in group 1 has a single positive charge. Iodide is I with a charge of 1 negative. So we have a single positive and a single negative. What happens? They cancel each other out, and we wind up with Ki. Then we have sodium carbonate, and we already wrote the formula for this. We have Na with a positive charge, and carbonate is CO3 with a 2 negative charge. We saw already then that this formula is Na2CO3. So when I write out the products in this case, we just simply, and the way we usually label it is as NR to represent no reaction. But now to predict this, here's how we would have predicted it. Let's say that we didn't know for sure, we didn't actually do it, and so we wanted to predict whether or not it would happen. So here's how you can predict whether or not a reaction would happen. Let's say that there would have been products, If there would have been products, potassium would have paired up with carbonate, and sodium would have paired up with iodide. And so the potential products would have been K2, CO3, and the other product would have been NaI. Because the N would be Ni positive with I negative. And these would have been the two potential products. Then what we would have done is we would have gone to our solubility table. We would have looked up the solubilities of these products. We would find potassium right here. And all compounds containing potassium are soluble with no exceptions. If it's soluble with no exceptions, that means its phase label would have been AQ. And sodium iodide, had we done it, anything that contains sodium is soluble with no exceptions. If it's soluble with no exceptions, phase label is going to be AQ. So here's how we could have predicted that there would have been no reaction. Oops, and then we forgot one phase label here. The phase label we forgot was for the sodium carbonate. That was aqueous as well. But here's how the rule works. It says if we start with two aqueous ionic compounds, and the products show that we would form two aqueous ionic compounds, then there will be no reaction. So again, if we start with two aqueous ionic compounds, and the products show the two aqueous ionic compounds would form, then we will have no reaction. And so we could have predicted this in advance that nothing would have happened. So I'll repeat it one more time in case you're writing this down. If we start with two aqueous ionic compounds, and the products show the two aqueous ionic compounds would form, then we have no reaction. Yes?
So on an exam, would you want us to like show all that work, or would we just be able to write like no reaction?
Well, here's how you could think about it more rapidly. I'm trying to address your question as briefly as possible. Basically, if you have a potassium compounds will always be soluble with no exceptions. Sodium compounds will always be soluble with no exceptions. So if you're reacting a potassium compound with a sodium compound, you're always going to have no reaction. And so there's really not a whole lot you'd have to show if you wanted to explain the answer. If it was simply to write out complete balance equation, you could simply put this. If I said to explain your answer, then what you would say is that, well, a potassium compound combined with a sodium compound will always be no reaction because they're always soluble with no exceptions. And that would be a very simple way to explain it. Okay, any others? Yes?
Will we be able to use this table on the exam?
Yes, this is going to be provided for you on your exams. Anybody else? Okay, so here's some stuff to practice. And these will be the next 3 showing up on your Socrative app. First of all, we have lithium phosphate. I'm going to put these down here just a little further. Lithium phosphate. Aqueous, reacted with potassium hydroxide, aqueous. Yields. Then we have magnesium sulfate, reacted with calcium bromide, aqueous. Yields. And then the last one is going to be ammonium phosphate. Reacts with barium chloride, aqueous. So your assignment is this. Your assignment is to complete and balance these three equations. Complete and balance these three equations, showing the correct phase labels for the products and balancing the equation. One of these three will be no reaction. So one of these three will be no reaction. And so what I would do before you put in a ton of work is try to figure out which one is no reaction, and then complete and balance the next two. Four, three, two, one. And definitely, choice A with majority is going to be the one for which there's no reaction. And how could we look at this one very quickly and tell that there would be no reaction?
Lithium and potassium.
Yeah, lithium and potassium. So if these trade places, lithium and potassium compounds are always going to be soluble here with no exceptions. So that's a quick way you could eyeball this one and tell that nothing would happen. So check out the next couple. I think the next one is waiting for you here, the magnesium sulfate and the calcium bromide. If you have that one ready, you can lock that in. 5, 4, 3, 2, 1. Correct answer is choice B. The precipitate is the calcium sulfate. Now, in order to arrive at this one, here's how this particular one looks. There we go. We do our double replacement, and magnesium pairs up the bromide, calcium with the sulfate. So we have these as the two products, the calcium sulfate and the magnesium bromide. To come up with the phase labels, and this is where it will be tricky for some of you. If we don't have the phase label written in, we want to determine it on the sulfate. We then go to our table, our solubility table, and we find sulfates. Sulfate is under the category of mostly soluble. However, if we look at the exceptions, we see that when sulfate pairs up with strontium, barium, lead, or calcium, then it is insoluble. And because calcium sulfate is an exception, that must mean that it is labeled as insoluble, which makes it a solid. Then for the magnesium bromide, this one's easier, of course. We come back here, we see bromides are under the category of soluble. Magnesium bromide's not an exception, and so we would label it then as AQ. Any questions on that one? Then here's your last one. And we got 5, 4, 3, 2, 1. Correct choice is D. Now if you look at D and C, they look very similar, but if you look at the phase labels, you see that this one here shows barium phosphate as the soluble one, and this one here shows barium phosphate as the precipitate. So if you were to go ahead and try to work this one out and try to determine what those phases are, you would then see that the phosphates from your solubility table are mostly insoluble. Barium phosphate is not one of the exceptions listed over here, and so it gets labeled as a solid. This one here is ammonium chloride. Ammonium compounds are soluble with no exceptions, so it would have a phase label of AQ. Balancing in this one is a little bit more difficult, but what I'd suggest in this one is probably save the simplest formula to last, which is probably this one here. So now if you were to balance it, we could look at some of the different things to balance. Oh, and by the way, this should be a 2 here. So to balance it then, we could see that there's 1 phosphate ion here. There's 2 phosphate ions in this formula. So since there's 1 here and 2 here, the number that goes in front of the ammonium phosphate is 2. And then we go over to the, I don't know which one would be next. I guess we could just as well look at the ammonium ion. How many ammonium ions do we have altogether now? 6. How many ammonium ions here? 1. So what do we need here? We need a 6 there. Then if we look at the bariums, we have how many bariums here? 1. How many here?
3.
So we need to put 3 in front of the BaCl2. And how many chlorines? 6. And how many chlorines here? 6. This then is a balanced chemical equation. So any questions on any of these?